application that's very on demand in the last years or decades is the wireless communication, right? So, like I always start my parts, I will talk to what motivated MathWorks, or what motivated our users to use the wireless communication related toolboxes, because we have the first, I would say, the first part where, sorry, the first part of our users that usually develop a reference algorithm, and they usually are the communication algorithm and signal processing engineers, and they will be using MATLAB or the 5G toolbox or the wireless LAN toolbox or the LTE toolbox, depending on their application. And on the other hand, we have our hardware designers or hardware engineers that are more on the simulation, synthesis, static analysis, static timing analysis part, and where they are trying to develop the digital hardware and physical implementation. And what we noticed is that there is a disconnect between the system level design and the design and the hardware design, which leads, as we always say, to a very long iteration on the workflow. We can detect some errors and bugs very late in the process, in the workflow or in the process. So what we like for the model-based design, like for DSP HDL, like for HDL code generation, we try to connect always all the groups that are it should be working together. We try to provide a unified environment in order for example, signal processing engineers and comms engineers to be able to have a unified also language and environment with the digital designers engineers. And we believe that to have an efficient workflow that connects algorithm and hardware design, we should have like a top-down approach where we can start with modeling and simulating the standards-based or hardware-ready algorithm together with the wireless application, and later on use HDL coder to automatically generate target-independent HDL code, right? So if we go back to our two pictures, the idea behind this toolbox, or the wireless HDL toolbox, or the workflow behind the wireless HDL toolbox, is to connect these two areas and these two domains. So with the wireless HDL toolbox, we address, I would say, 4 specified application or implementation, but we also have where you can also customize your application. So what we will provide is some standard compliant HDL optimized blocks, like for the like what we saw in DSP HDL. We will have for the wireless HDL toolbox some standard compliant HDL optimized blocks, but we will also provide some reference applications, right? So you can use them out of the box ready, and you can also edit them if needed. So the majority of our blocks are white boxes, so you can go through the block and explore the implementation. Our reference applications are itself also some white models, so you can go and see how the application is implemented. And finally, we have some utilities for example, waveform generation and visualization, and how we can verify and compare the results. If we dive in a little bit in the details of wireless HDL, let's say you have a reference algorithm. Okay, here we are not talking about a specific application. You can choose your application or choose directly from the application that we have. We can add, of course, we can use the utilities for waveform to generate waveform or capture waveform, and finally use also the utilities for to verify the results. For our reference algorithm, we will be adding, the first step is to be adding a hardware architecture. So we will go from, like usual, we will go from a MATLAB representation of our model, of our algorithm, even have a more detailed or implementation-oriented algorithm in MATLAB. Later on, we will go to we'll go into Simulink. Like I said, Simulink is very adapted and is very adapted and very good into exploring timing, for example, through the sample times that you can change easily in Simulink. You can start conversing in sample processing rather than frame processing if needed. And the idea is to go from MATLAB to Simulink, but at the end, you can also convert or capture the results that you have in Simulink to MATLAB in order to verify the results and compare what you have at the algorithm level to what you had in the implementation level. So this iteration is the same that you would have in, and what we saw in DSP HDL or HDL independent application independent examples. The idea behind all these workflows is to have some data, validate the algorithm, verify the results, later on pass to a more detailed representation and hardware, a more hardware-friendly implementation in Simulink, explore the timing, the sample processing, and later on the verify and have this back-to-back testing always. So if we, that's actually a pulse detector that we have. You can see it's part of the example that I showed earlier, where you can see that you can easily detect with an algorithm in MATLAB a pulse. Later on in Simulink, if you need to have a Simulink representation, if you simulate your Simulink representation, you can also visualize and verify the results before going back to MATLAB. And the conversion between MATLAB and Simulink, or the frame-based, specifically about the frame-based and the sample-based processing, it could be done using the control signal, where you can see that the frame could be streamed as sample using, of course, the start and invalid or the control signals that you have. So this will be also reducing the effort needed in this conversion between the MATLAB or the frame-based domain and the sample-based domain. One of the last steps before going to implementation is exploring the data types effect, the data type effect on our architecture. So let's say that, of course, like I said, we are always modeling in either in MATLAB and our first models in floating point. Later on, we need to see how the fixed point quantization is affecting our model. So we can go and let, for example, for a first iteration, let fixed point designer go through all the conversion that is needed, but later on we can go and explore the effect of this conversion on a subsystem level or on a block level, and you can add some also some pragmas that are added later on in the code, where you can ask the synthesis tool later on to map, for example, this multiplier on DSPs. We can manually change also the output data type that you would have, or the input or the output data type for some for your subsystem. So you can limit your you can limit the data types that is input on the input and the output of your subsystem using these convert blocks. Once we are happy and we validated our fixed point representation of the model, we can go through the code generation. So for generating code, we will go also and use HDL coder. So it's the stepping stone of all the, even the application oriented toolboxes that we have. We will always have the need to go back to HDL coder. With that being said, we will be always able to use the optimizations that are provided with the HDL coder, like resource sharing, pipelining, running on clock rate or data rate. So, and once you generate HDL code, you could later on verify this code, and we will see how. So you will be having a target independent HDL code. It's a readable code. If you go, even you don't need to go through the whole workflow. If you go to our documentation and see the code that is usually generated is readable and traceable code, and even it could be traceable to any requirements that is provided early in the stages of the project. So we said that it's a target independent code, but this code could be directly also implemented on some board. For that, you will be needing a hardware support package that we usually provide for the popular prototypes board that we have on the market. Or you can also import your own reference design to use it in order to target directly your development board. So let's see, I will visit the 5G LTE and wireless LAN standard and what we have here in our what we provide out of the box with the wireless HDL toolbox. For 5G, like I said, we have the reference application and we have some 5G compliant optimized HDL optimized blocks. And for these blocks, you will have also some metrics on once they are implemented and deployed on hardware, the type of the usage that they will be having. These some examples that we have for the applications, for the 5G applications, sorry. We will be having the same type of support for the LTE applications as optimized blocks, compliant blocks or reference applications. Like I said, these reference applications are it could be edited. It could be seen as a model, as a base model, Simulink model that could be used as a reference, and later on it could be edited if needed. And finally, we have some wireless LAN optimized blocks where they can be used in order to construct or to create your own Simulink model for your to be compliant to the standards that you are to the standard in use, right? So this is the part of the list of the blocks that we provide. Like I said, in our documentation, you can find more examples, more reference application, and more optimized blocks. So I invite you to check our documentation. There's a lot of explanation also of the theory behind each block, and the metrics that a lot of metrics will be provided for after the implementation for each block and for each optimized blocks. So it really gives you an idea to start what to use, how to use it, and the trade-off that you will be needing to have.